So in this video, we're going to talk about some of the most common types of radioactive decay. I mentioned in a previous lesson that some nuclei are stable, some other isotopes are not stable. Those not stable isotopes are what we call something that is radioactive, or what we mean when we say something is radioactive. So radioactive means contains unstable nuclei. So radioactive decay is the process by which nuclei become more stable, essentially. So the process by which unstable nuclei emit some combination of particles and energy, so particles and or energy, to become more stable. And there are 5 different types that we are going to talk about. Oops, forgot a word, apologies. Radioactive decay is the process by which unstable nuclei emit particles and or energy to become more stable. And there are 5 common types. Of radioactive decay. So the first one is known as alpha decay, where your nucleus emits an alpha particle. Which we said previously was the same thing as a helium nucleus. So it has a mass of 4 and an atomic number of 2. So an example of this is uranium-238 undergoes alpha decay to become thorium-234. So we can see that the atomic number is going down by 4, or sorry, the atomic mass is going down by 4, the atomic number is going down by 2, and our alpha particle is spit out as a separate product. So alpha particles are the largest particle that will be ejected from the nucleus. Because of this, alpha radiation is relatively easily blocked, so it's not very hazardous. Basically, like your clothing or even a sheet of paper or something in between an alpha radiation source and your body is enough to protect you, and even just your skin does a pretty good job. In order for radiation to do cellular damage, it has to be able to penetrate into the cells. And alpha particles are large enough that they don't get very far. So alpha particles, or alpha radiation, external exposure to alpha radiation, your skin does a pretty good job of keeping that out, keeping it from doing anything more than surface damage. Now, it can be accompanied by other more harmful types of radiation. Many things do more than one type of decay simultaneously. So something that's an alpha emitter might also emit other types of particles or energy as well that can be more harmful. But alpha decay by itself, usually not dangerous, unless it's somehow internal, unless the source of radiation is actually inside your body. Next up, we have beta decay, where your nucleus emits a beta particle, aka an electron. Now, if you think about this for a moment, this should seem impossible. When we talk about the nucleus, we say that the nucleus contains protons and neutrons. The nucleus does not contain electrons, but somehow it emits one. And that's because the identity of the subatomic particles is actually changing in this process. That what's happening in order for an electron to get spit out of your nucleus, which should sound weird, because it is weird, is that a neutron is actually splitting into a proton and an electron. The proton stays in the nucleus because protons belong in the nucleus, and the electron gets spit out. So just in terms of that sort of one particle, we're starting with a neutron to see how this actually does in fact work. Splits into a proton and neutron. Reminder, beta particle and electron are the same thing. We can see that on the left we have a mass of 1. On the right we have a total mass of 1. On the left we have a total charge of 0. Positive 1 and negative 1 makes 0. So this is a balanced process. This works in the same way that any other nuclear reaction does. And an example of this is one that we saw in the previous video, where carbon-14 turns into nitrogen-14, plus an electron is given off as well. So we can see that our atomic number is going up by 1 when this happens. And that's because this process essentially creates a new proton from a neutron. Your mass isn't changing because protons and neutrons both have a mass of essentially 1. It's technically a little bit different, but your atomic number is going up because of that new proton in the nucleus. So beta decay is a little bit more dangerous than alpha because the particles are smaller, because electrons are much, much smaller than an alpha particle. It is easier for them to penetrate through materials, but it's still easily stopped by relatively dense things like most metals. So even like a sheet of aluminum foil would do the trick here pretty well to block that radiation from passing through. So a little bit higher energy can be more harmful, but still not a huge deal. Gamma decay is next on our list. And this is when your nucleus just emits energy. I say just as though it's not a big deal, but this is really the type of radiation that is most concerning because it is just energy. Actually makes it the most difficult to block. There's no physical object to be blocking. The energy can pass through most things. So basically you need like a really, really thick sheet of lead to stop gamma radiation from passing through. What else was I going to say? Lost my train of thought. Apologies. So gamma decay is actually capable of more significant cellular damage than most other types because it is very high energy. So it can cause different sorts of chemical reactions to happen in your cells that aren't supposed to happen, and that's when you get problems. And this also commonly occurs alongside the other types. So this is where, like earlier, I mentioned that alpha radiation really isn't a big deal, but sometimes alpha emitters are also gamma emitters, and then that's a problem. That these are gamma decay is really the most dangerous of the types that we're talking about. And because it's just energy, nothing about the structure of the nucleus really changes. The mass stays the same, the atomic number stays the same, it's just decreasing in energy. The fourth type is positron emission. So this is when the nucleus emits a positron. As you would expect from the name. So sort of like beta decay, where there were no electrons in the nucleus, but we created one, there are no positrons in the nucleus either. So a similar process is happening here, except this time it's a proton that's splitting apart instead of a neutron. Proton splits into a neutron and a positron. So we have our proton with mass of 1, charge of 1, splitting into a neutron, mass of 1, charge of 0, and positron, mass of 0, charge of 1. So once again, we can see that this is balanced. We have a total mass of 1 on both sides. We have a total charge of 1 on both sides. The neutron stays in the nucleus because neutrons belong in the nucleus, and the positron is emitted. So an example of this type of decay is potassium-38 undergoes positron emission to form argon-38, ejecting a positron in the process. So we can see here that our mass isn't changing because the positron doesn't have a significant mass, and our atomic number is going down by 1 in this case, because we've taken a proton and we've turned it into a neutron, so we're decreasing the atomic number. Because positrons and electrons are really, really similar, positron emission and beta decay are very similar in terms of their hazards and potential for cellular damage. So last but not least, we also have electron capture, where the nucleus actually absorbs an electron. So this is one where there's no particle being given off. There is usually energy released as part of this process, but we don't typically write it as part of the reaction. But our nucleus actually absorbs an electron from one of the atom's inner orbitals. And in this case, once again, we've got subatomic particles sort of changing types because that electron can't stay as an electron in the nucleus. What's actually going to happen is that a proton and that electron combine to form a neutron. So we're taking a proton and that electron that's being captured, it's kind of being eaten by the proton. Oops, wrong way. And the positive charge from the proton and the negative charge from the electron neutralize one another to get a neutrally charged neutron. Mass is still 1 because we started with the proton, which has a mass of 1, and the electron, which has a mass of essentially 0. An example of this one is argon-37 captures an electron to become chlorine-37. Yep. So once again, our mass isn't changing because the electron doesn't have a significant mass. But our atomic number is going down by 1 because once again, we're taking a proton and we're turning it into something else. We're turning it into a neutron. So, what was I going to say? I think that's all, actually. Those are the 5 main types of nuclear decay or radioactive decay.